my dear students and viewers. I welcome you all in this lecture on the topic of constraint qualifications. We noticed that in the last few lectures, we were talking about optimality conditions for constraint optimization problems. We have found the necessary optimality condition that if a point is a local minimum point of a constraint optimization problem, then that point might not be a KKT point unless and otherwise certain regularity condition is satisfied. This regularity condition satisfying which a local minimum point is going to be a KKT point for a constraint optimization problem is called constraint qualification. We notice that in deriving the KKT necessary optimality condition, we have used the condition that at a local minimum point, the dual cone of the linearizing cone and the dual cone of the tangent cone must be identical. This regularity condition is named as or is called as Guignard constraint qualification. Instead of this Guignard constraint qualification, there are several other regularity conditions also satisfying which a local minimum point must be a KKT point. In this lecture, we are going to detail and interrelate about several regularity conditions or constraint qualifications satisfying which a local minimum point for a constraint optimization problem must be a KKT point. Neatly, in this lecture, we will consider to talk about a few constraint qualification conditions for constraint optimization problems. In the discussion, we shall consider two kinds of constraint optimization problems. The first kind, where the constraint set is given by some inequality constraints, and in the second kind, the constraint set is given by both equality and inequality constraints. If we recall the KKT necessary optimality condition for a constraint optimization problem, in the statement of the theorem of the first order necessary optimality condition, you will see that we have assumed that the point x bar, a local minimum point of the constraint optimization problem, and in addition to this local optimality of the point x bar, we also have assumed that the dual of the linearizing cone and the dual of the tangent cone, they are of identical set. And under these two assumptions, the point x bar is a local minimum point plus the condition that the dual of the linearizing cone at the point x bar is equal to the dual cone of the tangent cone at the point x bar. Under these two assumptions that x bar is a local minimum point and this condition, under these two conditions, we have seen that the point x bar being a local minimum point must satisfy the KKT necessary optimality conditions. And after deriving the result for KKT necessary optimality condition, I have given an example where we have seen that if we just go with this x bar is a local minimum point, discarding this condition, then the point x bar might not be a KKT point. For example, I gave this example that you go for minimizing the function x1 inside a constraint set where the constraint set is given by intersection of two circular disks, a circular disk centering at the point 1 1 and a circular disk centering at the point 1 minus 1 of unit radius. You take intersection of these circular disks as your constraint set and go for minimizing the function x1, then you will find that as this point 1 0 is the only feasible point, is certainly be a local minimum point, but at this point 1 0 the KKT necessary optimality condition is not satisfied. And therefore, even if the given constraint optimization problem is a convex optimization problem, it is not necessary that at the point x bar, which is a local minimum point, you will have the KKT necessary optimality condition satisfied unless and until a condition similar to a condition like this is satisfied. For this particular example, the example that I gave over here, you will find that the linearizing cone at the point 1 0 is having the dual cone the set of directions d1, d2 in R2 such that d2 is equal to 0. But if you find the dual of the tangent cone at the point 1, 0, you will find that this dual of the tangent cone is the null set, and therefore the dual of the linearizing cone at the point 1, 0 is not identical with the dual of the tangent cone at the point 1, 0, and hence this condition is not satisfied, and possibly thereby the point 1, 0 is realized not to be a KKT point. In order to ensure that the KKT conditions are necessary for optimality, a constraint qualification like this condition is necessary. Basically, a constraint qualification is an assumption made about the constraint functions that when that assumption is satisfied by a local minimizer, then that ensures that the local minimizer is a KKT point or that satisfies the stationarity of the Lagrangian function. However, the conditions such as these, the dual cone of the linearizing cone and the dual cone of the tangent cone, they are identical, is is very abstract, although extremely general, but not easily verifiable. Therefore, for practical problems, we will try to find certain regularity assumptions, which are called as these constraint qualifications, which are more specific, easily verifiable, but maybe somewhat restrictive. But it's okay. Restrictiveness are a bit okay, but still the conditions should be such that they are easily verifiable, not like this one. You notice that to verify this condition, we need to identify neatly the linearizing cone, the tangent cone, and identification of linearizing cone, tangent cone, and their dual. For a general constant optimization problem is not really an easy task. We have seen that how difficult it is to identify the tangent cone, dual of the tangent cone, and so on. So in this lecture, we will try to find some other way outs that apart from these abstract, extremely general condition satisfying which a local minimizer is going to be a KKT point, we will consider some easy conditions satisfying which a local minimizer is also going to be a KKT point. We shall bifurcate these conditions to be talked into two parts. In the first part, we shall consider the constraint problems, where the constraint set is given by only inequality constraint. And in the second case, we will consider the constraint set is given by mixed type of equality and inequality constraints. Before getting into the conditions, let me just write out what do we mean by constraint qualification, which we commonly abbreviate as CQ, and note that the CQs or constraint qualifications are not of satisfying the constraints. It is not like you find some points X that are satisfying all the constraints or all the inequalities or equalities in the constraint. It is not like that. Constraint qualifications are basically assumptions on the constraint functions, that is on the functions gi's and h's, that when satisfied at a local minimizer, then it ensures that the local minimizer must be a stationary point of the Lagrangian function, or the local minimizer is a KKT point. Now next, for the moment we consider the case when we only have inequality constraints. So for the time being, at first we consider the constraint optimization problem that is given by, say, minimize a function fx of several variables subject to gix is less than equal to 0 for I is equal to 1 to till n. And here we assume that, as usual for first order necessary optimality condition, that f is a C1 function and all GIs are also C1 functions. Now, as the affine constraints poses fewer problems than nonlinear constants, we partition the set of inequality indices, that is this set of indices, let's suppose capital I, which is these numbers 1, 2 till m. We partition these set of indices capital I into two parts, into linear indices and nonlinear indices. Where for these linear indices I mean those indices for which gi is a linear function, and the nonlinear indices are those i's for which these gi's are nonlinear functions. So we partition these set capital I into two parts. I is equal to say I1 union I2, where I1 consists of the indices corresponding to the nonlinear functions, that is corresponding to those indices for which the function gi is nonlinear, and I2 consists of the indices corresponding to the linear or affine constraints. Now, corresponding to this partition, I1 and I2 for the set capital I, we also considered splitting of the active set of indices in terms of I1 and I2, which is as follows: that corresponding to this partition of capital I, we split off the active set of indices at a point say x naught, at a feasible point x naught, into two parts given by a1 at x naught, which is your I1 intersection ax naught, a2 x naught, which is given by I2 intersection ax naught. We notice that union of these a1 and a2 is the set A at the point x naught. With the help of this a1 and a2, we will now focus on the following constraint qualification conditions. The first constraint qualification that I would like to mention is the usual condition, the condition that we have taken up in the derivation of the KKT optimality condition, that the dual of the tangent cone is equal to the dual cone of the linearizing cone. This constant qualification is known as Guignard constant qualification. The next constant qualification that I would like to mention is the Abadi constant qualification, abbreviated by ACQ, which is that the linearizing cone at the point x naught is equal to the tangent cone at the point x naught. We notice that if the Abadi constant qualification is satisfied, then obviously the Guignard constant qualification also will be satisfied, because once this equality of sets are happening, then obviously their dual cone will be identical. However, the reverse might not be true, that if the dual cone of two sets are equal, then it might not be true that those two sets are equal. And hence, if we assume that x bar is a local minimizer plus this Abadi constant qualification instead of the Guignard constant qualification is true, then also the point, the minimizer, this point x naught, is going to be a KKT point. I would also like to mention one of the famous constant qualification, that is the Mangasarian-Fromovich constant qualification, which takes up the condition that there exists a direction in Rn such that we have the gradient of those GIs for which I is belonging to A1 x naught. We have the gradient of GI x naught transpose D is less than 0 for all I belonging to A1, and the gradient of those GIs for which I is belonging to A2 x naught, that is those GIs which are affine, for them we must have here less than equal to 0. So for nonlinear constraints you have this condition, for linear or affine constraints you should have this condition. If there exists certain D in Rn such that these two conditions are satisfied, then we call that the point x naught has satisfied the MFCQ, the Mangasarian-Fromowicz constraint qualification. And one more constraint qualification that I would like to mention here is, although for a convex optimization problem, but one of the simplest constraint qualification and might be one of the strongest constraint qualification, that is the Slater constraint qualification, which takes up the condition that all the functions, the constraints GIs, are convex and there exists a feasible point, say x hat, such that for all nonlinear constraints GIs, that means for all those i's, I belonging to the set I1, we have GI x hat is strictly less than 0. So crudely, x hat is an interior point to the non-affine constraints or nonlinear constraints, and x hat must be satisfying all the affine constraints. So some kind of non-emptiness of the interior of the feasible region is assumed in the Slater's constraint qualification. Therefore, geometrically, this Slater condition is associated to some kind of non-emptiness of the interior set, and this GCQ is already a geometric condition that the dual cones of the linearizing cone and the tangent cone must be identical. This AVD constant qualification is also some kind of geometric condition. This Mangasarian-Fromowicz condition is geometrically signifying that the intersection of these half spaces, you notice that geometrically this is a half space, right? This is also a half space. Intersection of all these half spaces is non-empty. That is the geometry of this Mangasarian-Fromowicz constant qualification. And you know, there is a nice interrelationship among all these four constant qualifications, although I'll not prove, we do not have much time to prove them, but I will just mention that this result, that this Slater constant qualification implies the Mangasarian-Fromowicz constant qualification. Mangasarian-Fromowicz constant qualification implies the Abadi constant qualification, and ultimately Abadi constant qualification implies the Guignard constant qualification. So Guignard constant qualification is extremely general, the most weak among all these four conditions, and the Slater constant qualification is the strongest, and therefore if the point x naught is a local minimizer of a constraint optimization problem, and at the point x naught if any of these four constant qualifications are satisfied, then we notice that as all of them are implying the general constant qualification, the Guignard constant qualification, therefore the point x naught being a minimizer plus a constant qualification among these four conditions will imply that the point x naught is a KKT point of the constraint optimization problem. For a proof of this result, you please look at the book by Forst and Hoffman entitled Optimization Theory and Practice, which came out through Springer in the year of 2010, which I have mentioned quite a few times in the earlier few lectures. If you please look at the page number 55, there you will find a detailed proof of this result. Although I don't like skipping proofs because there is no meaning if I don't give the proof of certain results. Just mentioning of certain results will not actually give a strong knowledge about what is actually going on inside of all these constant qualifications. But as we are running out of time, please excuse me. And if you're interested, you please look at the proof given in this page number 55. Now, next we will consider the general case where there may also occur equality constraints. In this context, I consider the general problem. The statement of the problem is as follows: that minimization of a function of several variables subject to gix less than equal to 0 for I belonging to capital I consists of the indices 1, 2, 3 to till n together with hjx is equal to 0 for j is equal to 1 to till say l, and you consider x is belonging to Rn as usual. Now for this optimization problem, one of the commonly used constraint qualification is the linear independence constraint qualification, or popularly known as LICQ, where by this LICQ we mean at a given feasible point x0, the vectors gradient of Gix0 for I belonging to the active set of indices at the point x0, this set of vectors together with the set of vectors gradient of hjx0 for all j is equal to 1 to till m, union of the vectors of these two sets are linearly independent. For this constraint optimization problem, this general optimization problem, we also have the Abedi constant qualification. We also have the Guignard constant qualification. They are as usual. That in the Abedi constant qualification, we have the linearizing cone at the point x0, a feasible point, is equal to the tangent cone at the point x0, and in the Guignard constant qualification, we have the dual cone of the linearizing cone is equal to the dual cone of the tangent cone at the point x0. These Abedi constant qualification and Guignard constant qualification are also applied for the general constraint optimization problem. We also have a, a weaker constant qualification than this Abedi constant qualification and Guignard constant qualification, that is Arrow-Hurwitz-Ujua constant qualification, which we abbreviate by AHUCQ, Arrow-Hurwitz-Ujua constant qualification, which is actually the Mangasarian-Frohovitz constant qualification version for this general problem with equality and inequality constraints. AHUCQ condition is as follows: that there exists certain D in Rn such that we have, for nonlinear inequality constraints, we have this quantity is less than 0 for all I belonging to A1x0, and for equality constraints we have this quantity is equal to 0 for every j is equal to 1 to till m. And together with this condition, we have that the gradient vectors corresponding to the equality constraint, this set is linearly independent. That is your A is your constant qualification. And the result interrelating this AHU, CQ, ACQ, GCQ, LICQ, all these constant qualifications for this constraint optimization problem involving equality and inequality constraints, we have the following result that the LICQ is the strongest. LICQ implies AHUCQ, which implies the Abadi constant qualification, and Abadi constant qualification implies the Guignard constant qualification. For a proof of this result, you may please visit the same book by Forst and Hoffman on the page number 56. There are also a few constant qualifications for these general optimization problems, general constant optimization problems involving equality and inequality constraints. Those I am not mentioning. If you are interested, you may please look at the fabulous discussion given in the chapter 5 of the Vajra Seradisetti's book, where you will find that there are few more constant qualifications like the Kotel's constant qualification, like the Kuhn-Tucker constant qualification, the same Kuhn-Tucker persons who have derived this Karush-Kuhn-Tucker optimality condition. There is also a Kuhn-Tucker constant qualification, and you will find that this Kotel's constant qualification implies the Kuhn-Tucker's constant qualification. Kuhn-Tucker's constant qualification implies the Abadi constant qualification. Abadi constant qualification implies the Guignard constant qualification, and the Mangasharian-Fromovich constant qualification for inequality constant problem, and the AHUCQ for the problems with equality and inequalities. They are equivalent with the Kotel's constant qualification. You please look at for this general discussion the chapter 5 of the Bazara-Serali book. You will be enriched with the constant qualification topic by looking at this fabulous discussion, a detailed discussion, and their interrelationship of several constant qualifications in this chapter 5. With this very short description of constant qualification, I now stop the lecture here, and this lecture eventually finishes the unit 6 of this course, theory for constraint optimization problems. In the next lecture, we will get into a new topic, the duality theory, Lagrange duality theory for constraint optimization problems. That is your unit 7. And once we finish the unit 7, we will get into methods to solve constraint optimization problems. Thank you. Thank you all for all of your kind presence.